Okay, so we're talking about planning now. Remember, we're in this third hunk of the class. We did search, we did logic, now we're doing planning. And we're trying to be better than assignment 1. Assignment 1, you wrote a planner, right? So, where do I want to be? Let's start here. Let's not start here. Well, yeah, okay, fine. Let's start here. So we want to be better than the first assignment. So the first assignment, you wrote a special purpose planner. You hard-coded in the state. You hard-coded in a heuristic. Fine, good. And you wrote a planner, planned where this little rover guy is going to go. If you're a grad student, you even managed to get it to fill up on battery juice. But it's not general purpose. A lot of people think that planning is like fundamental to intelligence and therefore comes up, people do it in a lot of different situations. Maybe there's some general purpose planning facility people have or that it would be cool to study. So people invented this thing called domain independent planning where you write down the planning problem and then you have a program that reads in the description of the domain. And then the question is, where does the heuristic come from? And that's what we were talking about last time. We met. We were talking about heuristics for planning. So how do we derive a heuristic? And someone suggested, I suggested h equals 0. Someone else suggested the number of unachieved goals as a heuristic. And what's wrong with that? Why not?
Because you can technically satisfy multiple goals.
I win the jackpot. I am rich and famous all in one move. I love that. I love that. If you have any tickets you've already bought, let me know. So that's a way of computing a heuristic. This end of lecture question hits it right on the head when the author asks, so the planning graph is just a tool for computing heuristics? Yes, sirree. Absolutely. It's just a tool for computing a heuristic value, which is the number of steps to go, the cost to go to reach a goal under a node. We're doing forward state space planning. So we start off in the state represented by the initial state, and we have kids representing actions, and we're going to try and find a goal. And how long till a goal? Well, we need some kind of heuristic. We talked last time about H1. Everyone remember H1? Tell me you remember something about H1. Doesn't have to be a lot. Let's do an example. Yeah, basically. Yeah, that's pretty good. Let's do an example for Cake World here. Everybody got Cake World? You want to have your cake and eat it too. A classic problem, which I face in my household. I don't know if you face it in yours. I hope so. Okay, so there are layers. In fact, so the thing we built actually with H1 is actually not a real planning graph. Today I'm going to talk about real planning graphs. First we'll do what H1 does, and then I'll tell you why it's not really quite as awesome as it could be. So we start off, I'm going to abbreviate a little bit. So we start off having a cake, and then, yeah, just like someone said, was it Dylan? We just imagine doing all the things you could do. And one of those things is going to be eating, I think. So here's the action of eating, and it's got as a precondition having the cake. And eating the cake gives you two things. It gives you not having the cake, and it gives you having eaten the cake. So we've got a fact layer. This is t equals 0, and then this is t equals 1. So we've got a fact layer, an action layer, and a fact layer.
Don't we propagate like a no-op?
Oh, yes, sir. Yeah, and I've been debating how to draw that, because there are tons of these little stupid no-op actions that drive me crazy. And how do you draw them? Let's try making a little teeny action like that, and if I get sick of it, I hope you'll forgive me. So if we do the no-op action, then we can actually have cake in the second time step, which is cool. Now there's another action in this cake domain, right? Eating. What are the preconditions of eating? Sorry? Or I'm sorry, baking. Baking is the other action. Baking. What are the preconditions of baking? Not having. So baking is not applicable in the initial state. These don't really represent states. This just represents these fact layers in this thing that's like a baby planning graph. Let's call it the reachability graph. Yeah, let's call it the reachability graph. Can you reach a particular literal? Like, I really want to get to the state where I've eaten a cake. Oh, I love those kinds of states. Actually, for some reason, I don't know about you guys, I enjoy the eating of the cake more than the state after I've eaten the cake. Like, I wish I could just keep eating the cake all the time without being in the state where I have just consumed a whopping lot of cake. It's actually less pleasant, I think. But anyway, we're not modeling that in this particular codification of the domain. So there's this baking action we can do. And so we can't bake until you not have a cake. So that's a precondition, is the not having.
We've already achieved our goal in P1.
Yeah, look at that. We have. Yeah. So computing the reachability graph is just this thing of looking at what you've got, looking at all applicable actions, doing all applicable actions, seeing what you can get in response, and no literals are ever taken away. I like to say that, people like to say things like, nothing's ever deleted. You ignore the deletes. It's true that you do, all of these negative literals come into the graph, this not having, but the not having doesn't diminish your having. It's like, this is the world of perfect harmony where we can all have what we want, even if it impinges on other people. If there's someone who really wants to have the cake, but I want to eat it, we're allowed to both do that. And so I think in the pseudocode for H1, which is in the other lecture, we keep going around this loop where find an action that has some literal that just became true as a precondition, then if the action is truly completely applicable, do it and record all the new things that have become true. And you go around this loop until all goals are true. So, yeah?
The Q is just like some kind of, just a bunch of literals, right?
Yeah, so let's talk about the Q. The Q here, literals that became true at T. So there's this rippling effect, right, where at some particular time something will become true, and you push it into the queue so that at the next time step you can go and figure out its ramifications. Notice that we have Q and Q prime here. So Q prime is the Q for the next time step. So if something like I ate the cake at the previous time step, now not having has become true. That's going on the next time step. That's going to enable baking. Baking is going to become applicable, an applicable action.
So we don't include in that literals that were already true in previous time steps?
Right. Exactly. If we look through this code, the only time things ever get added to Q is all the literals true in the initial state go in the first Q, and then Q prime is empty, and we only add something to Q prime if it was not already true. So these are the newly true literals. It's just a little more efficient that way. I mean, you could go and look through all actions all over again and see if they make anything true that isn't true already, but you might as well only check the actions that involve something that just became true recently. Sometimes, remember, I think I recommended for assignment 3 that you ground all your actions. So you've got go hardware store drill, you've got go drill bananas, you've got all these actions that you would personally never consider. So like the branching factor could be in the hundreds. So like checking all the actions all the time is a big pain in the neck. So speeding that up is important if you want an efficient implementation.
When we're working on the assignment 3 milestone, and we unify things when we want to, like that doesn't. I always fear unifying my two clauses or literals together for fear that I'll lose any original value. Is there any fear of doing that with the unification rules that you've given us, or that we talked about?
You're using this loaded word, unification.
Specifically, I remember there was a wonderful list of things that you would do and all the permutations to it.
Yeah, so that's the artificial intelligence, scientific field. It's a byproduct of human activity. It's thereby imperfect. In the early days, when strips was first invented, people did actually suggest using theorem provers to solve strips problems. So the reason we have these operator schemata with parameters that look just like variables and you're really tempted to call it unification is because people did used to do unification, and it was very general. And you have function symbols and like first order logic, and it was like craziness. Strips itself is actually a little more constrained. There are no function symbols anywhere. There isn't universal quantification or existential quantification symbols anywhere. So it looks a little like first order logic, and it feels a little like first order logic, and we might even use sometimes terms like unification, but it's not really first order logic. It's not nearly so complicated. All you have to do is this grounding where you substitute all possible terms in for the arguments, but because there are no function symbols, the terms are trivial. They're just constants. So you have to substitute all possible combinations of constants in the operator schemata to ground them out, to ground actions, or at least that's what I recommend you do in your assignment. But worrying about unification and the occurs check and renaming and all this crazy stuff, you don't have to worry about it. It's way simpler than that. So no worries. Fear not, for behold, we merely substitute constants. You do have to, if you have an operator description, here there aren't even any variables. This is a pathetic domain. But if we've got, don't we have the hardware store somewhere? Yeah, here we go. Like these had better be the same here, right? So in that sense, the precondition of being at here and the postcondition of deleting at here, those had better be the same here when you substitute in the constants. So yes, you do have to worry about that. But that's a pretty minor concern. Yeah, I'm sure you can handle it.
It's stupid, but terminology. What's the word for things that aren't constants, the things on the outsides of the parentheses? Like at or cells?
Yeah,
predicates. Okay.
Predicates, yeah. Predicates, yeah. And the whole thing, yeah, I don't have like a section of the lecture that's like, here's first order syntax. I just start using the words because I feel like people learn naturally that way and it's less boring. But it's...
That's the confusing part because we use first order syntax, but it's not actually really first order logic.
Yeah, except that this is negated and that's a predicate and that's a variable. So this is, you'd call this a literal. This is a negative literal, that's a positive literal. So the terminology is kind of similar. Dylan was first with his hand, I think.
Store X and X can all be like the same thing, right?
I don't see no precondition that they're not equal. Yeah. If you want to do fancy, like beyond strip stuff, you could have a little type system and you could say that store has to be a location and X has to be a physical object or something. I guess the store could sell a service, so maybe X has to be a product or service.
I'd just rather buy a store in a store.
Go to the store. Yeah. 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 I have one of those wonderful UNHCS T-shirts that has the recursive shirt on it. And my kids always say, Dad, you're wearing the shirt. They just love that it's a shirt about shirts. You had your hand up.
Yeah, you can't have like ands and ors in there, can you?
Life is good.
So here, right there.
Here, there.
This is going to get real fun. So right where you are
There's a laser pointer here. You just push the little green button.
I didn't know there would be lasers.
It's AI, robots and lasers.
So, right there.
Yeah.
That here, you're saying it has to be the same as that here.
Yeah.
There.
Yep. It's as if it's as almost like, don't think this is like procedural or anything, but like it's almost like this is an argument and it gets substituted. Yeah.
Okay, so.
These are called parameters, I think.
All right, so in this context right here, this and this is the same. So every time but if it says here down here, we don't care.
Exactly.
All right, so in that context, it would be a little bit fancy to create a type system, like you were saying, have it. But so we don't have to worry about unification, but we do have to worry about consistency.
Yeah.
Right.
I would suggest not writing stuff that's wrong. Yeah. Exactly.
A triangle variable for go.
Yeah.
For scoping.
Everybody clear on strips? It's important. Now, I want to emphasize something that I'm...
Shoot the lasers.
We had a list of questions we were going to ask. I think we covered all of them.
I love it. Fantastic. Okay. Yeah. Strips. Initial goal. It's strips so that everything in the initial state that's not specified as being true is implicitly false. It's a known world. We know everything there is to know. However, the goal state is completely different. Anything that's not specified, you don't care. I want to be rich and famous. I don't care about the color of my house. Okay, it's not that my house is not blue and not green and not everything because I didn't say. It's just that I just don't care. I don't care if it could be blue, it could not be blue.
Specify, I want to be rich and famous and have a brown house.
Exactly. I really would not. I think brown houses are ugly. I'm sorry if anyone here has a brown house. What about what?
A pink house with green shutters.
Woo! That'd be like eye-popping. Only if it's like so bold that it's cool. Like if it's actually trying to be cutesy, no. But if it's like got pink polka dots painted on the outside, that is cool. You have to really overdo it though. Otherwise people will think you're serious.
So at the first, what is that, the H1 graph called again?
We're calling it the reachability graph.
Okay, so the first, whatever.
A fact layer?
Yeah, the first fact layer, doesn't that have to have the negative literals in there too, like not eat?
So not eat should be right here. Not eat. Haven't eaten it, and we do a no-op. God, I hate these graphs. Okay. I mean, that's the worst part of exam 2, is I make you do one of these by hand. And you're just like, where's my program? I need my program. Because these are the kind of thing computers were invented for.
Eat are not the same thing.
Eat is an action. And eaten is a, yeah, I'm using the same letter because I'm lazy. Is that okay? Okay. Yeah, if you hand this in on an exam for Cake World, I'll give you full credit. If I ask for a reachability graph. Yeah, there was something like that on this last test where somebody said something that wasn't quite right, but then we found a slide where it says exactly that, and so I had to give them full credit. Yeah, silly me for saying something slightly wrong. So yeah, it's a good point. You probably should put this negative thing in there. Yeah. The handling of negative literals has always been a little sketchy in the assignment, so we're trying to change it this year where you have to handle negative goals. So there's in these, unlike we give you sample instances and we give you a reference solution, all that, and that's all for last year, so it's all wrong. Matt is making a new version tonight. So this year, in addition to saying goal, we have something I think called goal neg, which consists of all the things that are negative in the goal. So here it would be like not in jail, not having broken laws, or something like that.
Why is that separated from the regular goals?
To make it easier for you to parse. So that's the only reason. I want to make your life simple because you have enough to worry about because you have to implement a reachability graph. And grounding.
So we should be thanking you.
Well, that's up to you.
But the reachability graph isn't really implemented like a graph at all, right?
Oh, wow.
I mean, it's just like you don't even save the past layers. You only have the most current one.
Print it out as you.
Yeah, well, you know what? That's a philosophical question. Is it a graph if I don't record something in memory that's an adjacency matrix? Does it still count as a graph? I find it incredibly empowering to think about the implementation as independent from the specification of the program. And you know, this is, for me, this is traversing a graph. Now, you know, is it building an adjacency list or an adjacency matrix? No. But is it traversing a graph? Yes. So, you know, however you want to think about it. Some people are more comfortable thinking that this is not a graph. This is just, you know, I don't know. It's what it is dynamic programming if you took the algorithms class. Anyway, what you really want is a hash table because you have to look up, you know, are the preconditions true? You have to record that something became true at a particular time. So for every literal, you want to store when it becomes true. You want to test whether all the goals have been achieved yet. So if you get a miss, you assume it's still an infinity. So that's what I'd use if you want to talk about implementation. Okay, but what I feel like I'm still want to say one more time about these underspecified goals. We'll tell you what has to be true, we'll tell you about what has to be false, and anything else we don't care. Okay? So there's this asymmetry in strips problems. Goal state fully known, initial state fully known, goal state partially specified. Okay, and we'll come back to that on Wednesday because it's important. Anything else? Okay. The topic for today is not H1. Goodbye, H1. The topic for today is planning graphs. Did I already talk about operator decomposition for parallel planning? I feel like I did. No, I didn't. Okay, I'll talk about this now. So does everyone understand reachability graphs? Okay, so you look at all the things that are true, you do all the actions, more and more things become true, and this is one cool thing about the reachability graph, is if you're looking up whether all the goal literals are true, and after a while this graph is going to level off, so to speak, like there won't be any more actions to do than ones you've already done. Like, hey, we've already eaten, we've already baked. I should draw the next fact layer, but there won't be any another action layer after this because everything that we can do, we've already done. If the goal of the problem was to achieve some literal that it's not mentioned here, we would know that goal was unachievable because the reachability graph has leveled off, and like sleeping has not been achieved by anything. So the reachability graph is awesome because it can compute h values of infinity and tell you that a goal is unreachable without you doing any search whatsoever. The first time you compute a heuristic value and compute the reachability graph, you'll be like, okay, where's sleeping? Graph is leveled off. I haven't gotten sleeping yet. Sleeping is unachievable. So that's a very cool feature of the reachability graph.